I want to give you a little bit of a demonstration about what P waves and S waves, how they behave. And so P waves, in fact, are compressional waves. They have an area of compression and then rarefaction after that. So the wave pulse itself goes forward and then it comes backward. Well, it doesn't really come backward. It just is less compressed behind it. And so we call that rarefied. And then the S waves are from side to side. And so I'm going to pluck this seismic wave demonstrator here. It looks like a slinky to you, but it's a demonstrator. And so I'm going to pluck it on the side then, and you'll see the wave travel in a different shape than what it does when it's a P wave. So the P waves go forward, and then the S waves go from side to side. So you'll see that in this demonstration. This is a singing bowl. This comes from, I think this one's from Nepal. Some of them come from Bhutan, some of them come from India and Tibet and a few other places. But a singing bowl, you create sound by rubbing the outside of it, and there's friction. And so the friction actually causes some resonance. And ironically, this is the same way that the Earth works in some ways. The Earth has faults, and there's friction that builds up on those faults, and then it ruptures spontaneously and generates an earthquake. And then those waves, like sound waves, travel through the Earth. And so that's kind of interesting. The It's a dispersion of energy, isn't it? Energy is the big deal. Energy and matter work together. And so what I want to talk with you today about is earthquake processes. When you have that rupture, the seismic waves move, they vibrate, just like sound waves in some ways. Some of them go as P waves, as you know, longitudinal waves, that's the P waves, and they travel like sound waves through, in this case, a medium. And so they go through the Earth, really, and people have actually indicated if you're around an earthquake and you actually experience it, you may actually hear the earthquake as well. Now, it's going to be a very low rumble if you do hear it, but it's not uncommon that people sometimes hear earthquakes. So if you have a place where the rupture occurs, that's what we're going to call the focus, and that's the place where all of the seismic waves emanate from. The P waves, the compressional waves, or the S waves, the ones that are shear waves, the ones that go from side to side. But they all emanate, they start at the same time, and they make their way upward if it happens deep inside of the Earth. And usually most faults break somewhere around 15 kilometers or deeper, usually, and all the way up to 600 kilometers, as you know. And so as they emanate upward, they eventually intersect the land surface, and there it begins to ripple on the land surface, and that's where you get the surface waves. And so, in fact, P waves and S waves get generated at the same time, and then surface waves afterwards. Okay, shortly afterwards, mind you, but a little bit after that. P waves travel much faster, the S waves travel a little bit slower, and then the land waves get generated at the Earth's surface from the epicenter. And so the epicenter becomes an important part of earthquakes at that point. So as you can see in this image, the very front image of this talk here, it shows a fault scarp. Now, a scarp is actually like a cliff that was made by fault movements, if you will. So if this is a fault and the fault slips this way, that's the fault scarp, the piece that was left behind where the other block of rock has slid down perhaps, or slid upwards perhaps. And they don't show you which direction it is on here, but they show you that that fault plane is kind of curved, and that the earthquake epicenter is not always located on top of the fault, the trace of that fault. We call it the trace of the fault. That's where the fault intersects the land surface. But in fact, because it's deep inside of the earth, the fault would have been generated along the fault, but in a buried location, and then the epicenter would be directly above it. And so that is the difference between the focus, which is where it ruptures, and the epicenter, where it seems to appear from, with land waves. And so the waves then would be generated, the surface waves at the top would be generated by that. But there's a whole series of wave fronts that go out, and it's kind of hemispherical, if you will, a whole series of spheres. So compression and rarefaction with the compressional waves. And the shear waves go side to side, right? That is an illustration of what it's like to have an earthquake. Now, these things can occur in a lot of different depths, as we just talked about. They can get all the way down to 600 kilometers. If you look at this diagram right here, this is the Walati Binioff diagram, and it shows you the Tonga Arch. Now, this is a place in the South Pacific, and it's close to the Marianas Trench, a little bit farther to the east from the Marianas. And it's a place, it's not too far from Tahiti also, so Tahiti's a little bit even farther to the east here. But it's a place where the Pacific Ocean's being subducted in that trench. And so there's ocean plate on the left-hand side of this diagram. That's on the west. And there's the Tonga Islands here. And then it shows you where it's being subducted. And they have detected earthquakes all along that distance through here. I'll show you a little illustration here in a second. But that is the location from shallow to medium depth in the crust all the way down to in the earth, in the lithosphere, all the way down to 600 kilometers deep, okay? But that's on the subducting slab as it goes into the mantle. And so that is the Walati Binioff zone, they call it. Binioff was an American. Walati was a Japanese scientist. And so they were geophysicists, and they studied this sort of thing. And you can see in the inset down here the location. It's a little bit farther north from New Zealand there. So earthquakes can occur all the way down to 600 kilometers, but it doesn't mean that's where the waves stop. The waves can continue on through the earth, and in fact, they go all the way to the core mantle boundary. And as we've already talked about, they hit the core mantle boundary, the P waves continue on and get diffracted a little bit. So it's like a glancing blow, if you will. And so those emanate outwards and form like and there's an area called a ring, right? So that's the P wave shadow zone around the bottom of the earth. I think it's 105 degrees away from the actual seismic event itself. And then I think it shows up again at like 138 or 140 degrees. And so there's a little gap where the P waves are not felt. And neither are the S waves in that gap. In fact, the S waves aren't felt anywhere on the opposite side of the earth. You have to get 105 degrees away from the actual epicenter from a seismic event in order, but that is the S wave shadow zone. And so you don't feel the S waves or the shear waves on the opposite side. What happens instead is the S waves penetrating through the earth hit that core mantle boundary where there's liquid. Well, the S waves can't travel through liquids, as it turns out. S waves, shear waves, cannot travel through fluids. They just can't do it. So what they do instead is they actually get converted into P waves. They actually go through what they call a phase change. So if it's going this way, it all of a sudden begins to go this way. And so that is kind of the behavior of the interior of the earth, I guess. We talked a little bit about that when we talked about the interior of the earth. So seismic stations are where we record earthquakes. Typically, it takes at least 3 seismic stations to be able to pinpoint the epicenter. Now, there's lots more than 3 seismic stations. There's thousands of them across the world. In fact, Japan alone has thousands of them, just to detect exactly where earthquakes have occurred. And so there's all of these thousands, you can actually pinpoint the distance to where that earthquake occurred. So if something snaps in one part of the world, you detect it in various areas around it, and the distance away from that epicenter is proportional to to the distance away from the earthquake, right? And so it takes a while for those seismic waves to travel through the earth and to travel to these other seismic stations. So the nearer you are with a seismic station, the more likely you're going to record it first. There's a funny behavior about that, so we'll talk about that in a second, because the waves actually go faster once you get inside of the earth. They go slower in the outer part because it's not quite so dense. And so where it gets denser, the waves tend to travel a little bit faster. So these seismic stations, we call them seismographs. They record seismograms. Seismograms are the actual register for these things. We talked a little bit about that with this Tohoku earthquake, and I showed you some of the seismograms from around the world there. Now, these instruments are isolated, and so the way that they work is there'll be an isolated mass, and then it moves relative to everything else. And, actually, everything else moves around it, and it stays pretty much stationary. These days, they're all mostly digital, but I got to tell you, you can actually get something like a seismogram on your cell phone. So I think it's called Epicenter here. This shows you the earthquake. So this is a neat app for a cell phone. Shows you where the epicenters are. But there's actually another one. It used to be called iSeismometer. I guess I don't have it on here anymore. But there's an accelerometer in your cell phone. So whenever you shake your cell phone, it will actually record the waves. And so it used to be called iSeismometer. Maybe I'm so cheap, right? So I don't pay money for my apps if I can get away from it. So anyway, that is kind of a couple of neat things. So the USGS records all of these earthquakes, and they report the latest earthquakes on their website. So if you just look up earthquakes, it's usually going to take you to the USGS. Now, the USGS is the premier research agency in the United States for looking at geology, but especially earthquake hazards. And in order to understand earthquake hazards, they have to have enough stations around the world, usually at universities and places like that. And so they record those earthquakes, and then they report it on their website. And so I think there was a 6 just a couple of days ago here. But anyway, there's a whole bunch of different apps that you can get that relate to earthquakes, and you can get some of them that'll actually use your cell phone as for citizen science, where it actually records some of the earthquakes and will report it if you're in a place where there happened to have been an earthquake. Kind of neat stuff. So seismographs, seismograms, isolated masses, the earth moves around it and it keeps it stationary more or less, but it detects the movement in 3 dimensions, so up and down, left and right, and then forwards and backwards. And so here's an example of what it would have looked like back in the 1960s when they were building these things, 1950s. So they have an isolated mass. You can see it here. It's called a suspended mass. And they have a spring, and there's a hinge, and so it would stay stationary while everything around it was moving. And then it recorded, in the old days, it would have recorded on a drum of paper that was continuous, more or less. We don't do it that way anymore, but instead what we use is digital plotter, essentially, that will record, as you've seen before already, 15-minute segments. Sometimes it's a shorter time length, but usually it's 15 minutes, and you can actually pinpoint exactly when the wave arrived there. The first wave that's going to arrive is going to be the P wave. Now here is an image that shows you this, and so if there is an earthquake that occurs, the P wave travels faster. And so the way to look at this, in fact, is if you turn your head sideways and you're looking at a more or less a flat line going upward, and that upwardness is time. And so time is the vertical dimension. And so as the earthquake record gets recorded here, it goes 1 second, 2 seconds, 3 seconds. I'm going upward on that scale now. And so follow the red line. So if you follow the red line, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, well, that's actually minutes, 7 minutes where it finally intersects where it actually is the first record, 7 minutes it took to get there. That's a long distance away then. And so if you follow it farther, you can see that it goes another minute, another 5 minutes, in fact, before finally the S wave shows up. Well, the P wave travels about 1.7 times faster than the S wave. And so it's like if you're driving from here to St. Louis, and the P wave, you would step on the gas and just get there as fast as you can. And with the S wave, you'd be driving it like this from side to side, right? So you're going to get there slower, right? So about 1.7 times faster if you had the P wave, okay, or the Porsche, let's call it, and S would be what? Whatever, Suzuki Samurai, right? So here you wind up a little bit slower. And so finally the S wave arrives. The distance between the S wave arrival time and the P wave arrival time, that tells you how far away you are from the epicenter, or actually the epicenter in this case, because usually the focus is not that deep, right? So in this case, you follow the blue lines back, and so if you're right there at the epicenter, you would feel one immediately and then the other one just after a little bit, right? But if you get farther and farther away, so in order to have that 5-minute span, you have to be about 3,800 kilometers away from the epicenter in order to feel that. And so that takes about 5 minutes, it says here. But anyway, that is the difference in the arrival times. And so from that, you can calculate how far away you are from the epicenter. If you have enough seismic stations, you can calculate that pretty rapidly. In the old days, they used to use seismic devices also to calculate what we call the Richter scale. So the Richter scale is a local amount of shaking, essentially, that would go on with a seismometer. And that's, so the Richter scale is not one that we use commonly anymore. So it only is used when you're right there on top of the earthquake. Instead, we use something called moments magnitude these days. And moments magnitude, we realize, is related to how much of a rupture zone there is. So if it's a large rupture zone, it's going to shake more, and so it's the moments magnitude, and so that shaking has a lot to do with that. So that's the P wave and the S wave, and how you would calculate, in fact, how far away you are from an epicenter. Takes longer for the waves to travel farther, right? Here, in this diagram, it shows you there was an epicenter, but in fact, the waves speed up if they're going inside of the Earth, and so they'll actually go faster inside of the Earth, and so sometimes they echo or they come back and get reflected upwards again. So you may actually feel the distant the distant earthquakes first in far distant areas. And then you'll get those shallow waves coming in later. It just shows you that it travels with higher velocity when you're deeper inside of the Earth. And this makes sense because as you get deeper inside of the Earth, the material gets more dense. Deeper is more dense, okay, until you finally get to that core mantle boundary. So in the next slide here is that illustration of where the P wave and the S wave shadow zones are here. So if you think about the P wave shadow zone, it's kind of a ring shape, okay? So if you think about the globe, if the epicenter was at the top of the globe, you would have a ring shape, sort of like a girdle around the bottom of the globe, 105 degrees away from that epicenter. So you'd follow the globe around to 105 degrees, and here's that ring shape. For the S wave, because the S waves can't go through the liquid outer core, that's going to be more bowl-shaped down here at the bottom of the Earth. Okay, so that is the difference between them. So you'll feel the P waves at the bottom of the Earth, but you won't feel the S waves. And for the P waves and if you're above that shadow, between the epicenter and 105 degrees away, you're going to feel both the P waves and the S waves. Probably not going to be a lot of damage or anything like that, but your seismometer will pick up the sort of shaking and everything because it's a very sensitive instrument. If you're right there at the epicenter, you already know what you're going to see if it's a large enough earthquake, or if it's shaking enough to knock down some really big buildings. And so we've talked about earthquake disasters already, and I don't want to dwell on that anymore because that's kind of the negative side of geology, but it's also something where we have a chance to actually save people's lives. That's what makes geology. When I first became a geologist, I thought, well, this is kind of selfish, because I really want to understand what's going on inside of the earth, but it doesn't help people. I could be a medical doctor or something like that, right? And I thought, that would be something. So geologists help people all the time. In fact, geologists can help stop pollution from spreading far away. We can actually help to predict when there are volcanic eruptions, and hopefully at some point we'll be able to more fully detect earthquakes before they actually can occur. And so that's one of the things that's really high up on the list for geologists and geophysicists to try to figure out is, can we predict earthquakes? We can kind of do it, but not very effectively. We can't say that this is going to be the day that we get an earthquake. Someday we might have that opportunity. So if we go to the Richter scale, let's say we're really close, to an earthquake. And the Richter scale is going to give us some sense of that ground motion. And it's with a magnitude 1 through 4, so likely you're not even going to feel it. I suppose, it's like you might feel like a 3.5 or something like that. I think that's the largest earthquake that I recall ever having experienced myself. I think it was a 4.5 actually. It was in Milpitas. I was working at the U.S. Geological Survey in Palo Alto, California, and I felt that the earth was moving a little bit, and I looked over at the window and I could see that the mini blinds were shifting. That little spindle, where you can close or open the mini blinds was shaking, and my chair was rolling along, right? I talked a little bit about the piano bench already. Well, she was stationary, and the room was moving around her, and so the wheels kept her stationary essentially on that. And so that's what the wheels were on my chair, kept me stationary as everything around me was moving. Magnitude 5, this is how we talk about it. We call it magnitude, right? Magnitude 5, most people are going to notice that. Some dishes are going to fall off. Magnitude 6, everybody feels a 6. Magnitude 7, people driving cars, all of a sudden you're driving in a car and you feel the earth, like people have told me, like the Loma Prieta earthquake was a 7.9, I think it was 6.9. It was huge, big enough anyway, that people told me when they were driving during that earthquake, and I knew people that experienced that earthquake, that it felt like they had 4 flat tires. It was moving that much. And so that's the sort of thing you can expect, I guess, out of driving during an earthquake, right? For a magnitude 8, it's going to cause some damage. Driving becomes difficult. Walls will crack. Chimneys begin to topple and things like that. Magnitude 9, the shaking intensity. One of the things that people who have experienced a lot of earthquakes tell me is that what they do is they begin counting as soon as they feel that first shock from that earthquake. And they begin counting, and if it starts getting over 20 seconds, 30 seconds, then they start worrying, because with the continued shaking is something that will shake buildings down. And so, for instance, I think the Loma Prieta earthquake shook for 50 seconds, 45, 50 seconds in Palo Alto. And I worked at an office that was affected by that. So people pay attention to that. It's like, is it time to go out now? If it's a little one, you don't want to get up out of your chair and run away quite yet. But if you can, get under your desk, get to a place where it's safe. Number 10, the magnitude 10s are so rare. In fact, we've never recorded a magnitude 10 in the moment's magnitude scale. Okay, so they have occurred in the past. We know that they have. We're pretty sure that even large, so I studied meteorite impacts, right? The estimate is you can actually get a magnitude 12 from a meteorite impact if it's large enough. So magnitude 12, if you think like a 9, which 9.5 was one of the largest ever recorded in the last 100 years here, right? So a 9.5 was enough to kill people thousands of miles away in Hawaii. And it threw boats, onshore in Chile. And so that magnitude 9.5 was absolutely enormous. It was magnitude 9 in Alaska, and that thing shook things too. there were fault scarps that formed that were 30 feet high at least. There was a 200-foot wall of water in one place where it was kind of a seiche that ran up the valley and then pulled all the trees back down into one of the fjords that's in South Alaska. Yeah, it's pretty devastating, these things. And so that is a Richter scale, but it just gives you a kind of a qualitative sort of aspect of what this Richter scale actually means. So if Richter is the local shaking, what we prefer to use, in fact, is the moment magnitude scale. And so that's directly related to how much the rupture was when it broke. And so we can look at that and say, oh, that was a large one. And so every time you go up a number, now this is really important actually, so I'm gonna face you right now and say, if you have a magnitude 5 earthquake, let's say a magnitude 4, you just barely feel it, right? A magnitude 5 is just a little bit larger, right? Not really. A magnitude 5 earthquake is 33 times larger. 31.6, I think, is the actual number, but 33 is easier to remember, and it's easier to figure out some calculations this way. Magnitude 4, you released 33 times more energy when it goes up to a 5. So put this into context here. We had a magnitude 9, right, in Alaska. How many magnitude 9 earthquakes would equal, how many magnitude 4 earthquakes would equal a magnitude 9? And it's easy to figure out. You just keep multiplying. So to go from 4 to 5, you have to multiply by 33. So 33 magnitude 4s is equal to a 5. 33 times 33, or about 1,000, 999, right, or roughly. That's how much it would take magnitude 6, or it'd take about 1,000 magnitude 4 earthquakes to equal 1 magnitude 6. And again, 33 times that, so 33,000 earthquakes of magnitude 4 is equal to a 7. And 33 times that, so almost a million is equal to an 8. Takes there's a million times more energy released by a magnitude 8 than there is a magnitude 4. And to take it up to a 9, that's 33 million. That's a lot of energy, okay, to go from a 4 to a 9. So every time you make that step, and in between, if you see like a 3.5, well, it's a logarithmic scale, right? So it goes up a little bit. A 3.5 releases closer to the amount of energy that you would have like a 4, okay? So that is how you relate magnitude from small earthquakes to large earthquakes. So in other words, in California, everybody expects the big one, right? And the fact is, if you experience a whole lot of small earthquakes, you might think that that would keep the big one from occurring. It's not the case. The stress still builds up, and the little ones don't release enough energy to make up and account for all that could be building up for a place that may eventually break and cause a massive earthquake to occur. So there will be massive earthquakes regardless of how many smaller earthquakes there are. There's that much stress, and the plates are that dynamic. Remember, they're only growing about as fast as your fingernails grow, but they're pushing against each other in a slab that's 200 kilometers thick, right? And they're running by one another, or they're being subducted, or they're colliding with one another. And so there's all these different sorts of attitudes or types of behaviors that they have at these plate boundaries. And so a massive amount of energy is released by really large earthquakes. There's another way that we try to describe how these earthquakes affect people, and it's called the lateral acceleration of gravity. So if you can imagine, you're standing in a place, and then all of a sudden, if the earth moves, it's as though you were in midair, and you will be slamming into a wall if it's a large enough earthquake. That is a lateral acceleration. Now, you didn't want to run into that wall, but the earth met you there, and you slam into that wall. that is a lateral acceleration. So they do this compared to gravity. Your body's being attracted by 1 to the Earth right now. If you can imagine, some of the larger earthquakes have a lateral acceleration like 2 or 2.5 or 3. And so it's like falling 3 times your height up against a wall. Usually it's a little less than that. It's like 1.2 or something like that. Pretty common. But, it's like it's hard to measure that sometimes, I think. There's one other scale that we use, and this is for the insurance adjusters. So the insurance agents come out after an earthquake. They inspect the damage, cut a check for whoever has earthquake insurance. Typically, it's an act of God if people experience earthquakes, and the insurance companies commonly won't repair it. It depends on if FEMA comes in and makes a low-cost loan available to you. You'll repair your house then. They come in, and what they do is it's called a modified Mercalli scale. And they actually have a list of terms that they use. So, okay, the chimney fell down. That's a number 6. And so they actually go out and they mark down the number. And that scale goes from like 1 to 12, I think it is, for how much damage there is. And so it's not something you can record directly at the time of an earthquake. It's something you would do afterwards to assess how much damage there was. Okay, if we talk about how much energy is released by really large earthquakes, in this table right here, you can see how much energy is released by a pound of explosives blowing up. You can see that a lightning bolt has 630,000 ergs of energy. And that's a measurement of energy. It's not very commonly measured, but if you had a lightning bolt, that's like a magnitude 2 earthquake, essentially. And you've probably heard windows rumble. You've probably maybe even felt the ground shake from a really close by lightning bolt. Maybe you've been around, hopefully you'll never be around a nuclear explosive, but some of the smaller ones, 1946 there was one, it equaled a magnitude 6 earthquake. If you take the Hiroshima, it's even smaller than that. So, and then Nagasaki was even smaller than that. You've seen the devastation from those bombs, those nuclear bombs when they blow up. The Northridge earthquake, we didn't talk about it a lot. We talked about the Kobe earthquake, but it was a 6, and it released a lot of, it was a magnitude 6, and so it released 630 quintillion ergs of energy. So they don't give you a nice, easy way to describe that. Normally, when we talk about energy, we talk in different terms than ergs usually. But if you follow the list down here, you can see the 1964 Alaska earthquake. That was the Good Friday earthquake. Here you can see that the Good Friday earthquake released more energy than the Mount St. Helens 1980 volcanic eruption. And then if you go down the list, the annual energy usage for all of the vehicles, all of the power plants, all of the airplanes in the United States is equal to a magnitude 10 earthquake. There's that much energy released by a magnitude 10. So, a lot of energy is released by earthquakes. It's not the only product that you get is the damage. We talked about this a little bit. We talked about liquefaction when we talked about earthquake disasters. I'm going to show you actually some liquefaction in that happened after an earthquake in India. And Gujarat province, it's a little bit north and west of Bombay, and there were 20,000 people killed in that earthquake, and another 6 million people were left homeless or affected and injured by that earthquake. But the earth shook so much from this earthquake. There was a nearby wetland area, and it actually had experienced what we call sand volcanoes. So the earth shakes, there's a rupture in the land surface, and then the sand-water mixture shoots out of the earth. And what you see is the before and after pictures here. So one satellite image was taken on the 31st of January. And if you look at the one previous to that on the 15th of January here, and you can see that there's a whole bunch of water that was released by that earthquake. And in fact, if you go to YouTube and you look up earthquakes, and you can actually see people walking along sidewalks. Sometimes water will start to pour out of those sidewalks as well. think those are in Japan. Many of the earthquakes there will actually have water released from them as well. Here's what it actually looks like on the ground. So this is that area. It's kind of a wetland area, and the earth opened up, and the sand has already flowed out of this, so all of the action's gone. Now it's just water boiling out of these fractures. But that's a sand volcano. Here's another image of a sand volcano after this. So these kind of features are very unusual. So you know that liquefaction is one of the products of the ground shaking here. Other things to stress with you. So we've talked about the lateral acceleration of gravity. We talked about the Richter scale. We've talked about the moment's magnitude scale. And we've talked about the Mercalli scale, the modified Mercalli scale, about how we quantify the damage and everything. We talked a little bit about how much energy is released by earthquakes as well. We talk about the ground shaking so much that you can actually have sand spewing out of the earth. That's one of the things that happened in the New Madrid earthquakes here in Missouri, is there were sand ridges that would develop. And after the earthquake, some people had said that they were like 20 feet high, some of the hills of sand that were erupted from the earth. It's an interesting phenomenon. I guess it'd be a lot more interesting if there weren't so many people killed in these sort of events. So it's not a good thing to have a large earthquake. As a geologist, I view it as like, a scientist, but at the same time, when you start seeing the images, it's like, wow, the earth is a perilous place. And we have earthquakes, we have volcanoes, we have meteorites that can come from outer space. Every one of these things can kill people. We even have diseases, as you well know now as well, that are easily can take out large parts of the population. And then we have self-inflicted things like wars and like people who don't have any meaning in their life, right? So people who are substance abusers and things like that, So there's 1,000,001 things that can kill you on this planet. Some of them are natural and some of them are self-induced. Best to keep it to the natural things, and even then to protect yourself as best you can to survive these sort of aspects of nature. So we're getting into the season right now, in fact, where we're looking at tornadoes, right? So I'm sure a tornado even has somewhat of a seismic sort of signature along with it. I think there's probably enough records of that in Oklahoma from some of the seismometers there that would show that there is some seismicity to, if there is seismicity to any sort of like lightning bolt, sure there's going to be some. It's associated with tornadoes as well. But the earthquakes we're talking about generated from fractures or ruptures in the Earth's surface where the rocks have reached their elastic limit and then they broke. And so where do they break? They break at faults. And so that's going to be the next place we go with this presentation, with this series of presentations. So that'll be before the next exam, but it won't be until next week that I get those uploaded. We're going to talk about faults and we're going to talk about other geologic structures next. So, yeah, thanks for hanging in here. Thanks for letting me try to recuperate a little bit from some of my ailments here, and I'm doing better now. So hopefully we'll be able to get this thing put behind us here. And so it's been a long semester, I gotta tell you, but I guess here's the record of me telling you as best I can the geology of the Earth. Okay, so every planet has a little bit of geology on it, right? So, but the Earth is the one that we live on. It's the one we have to care the most about, because if we don't take care to protect ourselves from the things that can happen naturally, there's a little bit of risk involved. So we want to minimize that if we can. Yeah, thanks a lot. Talk to you soon. Bye now.